Hey everyone, it's Ms. Butler. I got a video on intermolecular forces. We're going to break this down into kind of three main topics. So the first one is intramolecular versus intermolecular forces. So we want to be able to compare and contrast those types of forces. So the first is intramolecular forces, and this is what we've been studying at the end of first semester and into this semester. These are bonds. So these are within a molecule. I'm talking about if I have, something like water, I'm talking about the bond right there, holding the H to the O. There are kind of three main types we learned about: ionic, and then polar covalent, and nonpolar covalent. I gave ionic a star because really ionic compounds are actually kind of like attractions. Remember, we learned that they tend to make this crystal lattice structure where it's repeating positive, negative, positive, negative. So really, we're not going to focus too much on ionic forces, whether that's bonding or as an intermolecular force in this video. It's mostly about polar covalent bonding and then what those guys will do in terms of intermolecular. So intermolecular forces, I tend to abbreviate as IMF because I'm lazy, but those are attractions between molecule clones. So if I had my water and I clone this bad boy, I want to know about the attraction between the water molecules. Obviously, water must like other water molecules because we have liquid water all around Earth. If water didn't like each other, they would kind of float away from each other and we wouldn't have any oceans or anything like that. So I'm talking about the attraction between the molecules of water, between those clones. That's called intermolecular force. So let's talk about the different bonds, the intramolecular. We talked about ionic bonding. Again, it has a star because I'm not going to focus on it too much this video. So we're mostly going to focus on polar covalent and non-polar covalent bonds. Okay, so hopefully this is a little bit of a review, maybe some vocab, but I want to talk about dipole moments. So I'm talking about covalently bonded molecules, so atoms that are sharing their electrons. We learned that we can tell if it's polar covalent, unequal sharing, or non-polar covalent, which means equal sharing of electrons based off the electronegativities. Sorry about that. So I looked up the electronegativity of nitrogen and hydrogen, and the difference is when I subtract them is 0.9. So that means there's a difference of electronegativity on this bond of 0.9, on this bond of 0.9, and on this bond of 0.9. Because that 0.9 is between 0.3 and 1.6, that means it's a polar covalent bond. So the nitrogen is unequally sharing the electrons with each hydrogen. So how do I decide who's sharing, who's hogging the electrons the most? Well, I look at the electronegativities. The more electronegative is hogging the electron, so it gets a partial negative charge, partial negative. So I'll put that right here. And the element with the least or the lower electronegativity gets a partial positive because, again, those electrons are not spending a lot of time over here, so these guys are partially positive. When you have a molecule with a separation of charge, even if it's a partial positive and partial negative, we say that the molecule is having a dipole moment. So a polar molecule, like this guy, like this NH3 molecule, has a dipole moment because of the separation between the partial negative and the partial positive. So here's that NH3 molecule again. Sometimes instead of little partial symbols, they're going to use this arrow. Notice the arrow has a cross on one end. So where the cross is, that determines the partial positive. And where the arrow continues, think of that as like a minus sign right there. So here's your plus sign, partially positive. Here's your minus sign, partially negative. So you can see the way they labeled this. Your hydrogens are the partial positives and your nitrogen has that partial negative happening. Same idea with NF3. Now the difference though is fluorine is much more electronegative than nitrogen. So notice nitrogen is the partial positive and the partial negative is pulled towards the fluorine. So there are some molecules that have polar bonds but it doesn't always mean that the whole molecule is polar, meaning it doesn't always mean that there's a dipole moment in the molecule. Here's a great example, CO2. If you look up the electronegativity values, you'll see that there is a good difference, so that carbon and oxygen do not share equally, meaning oxygen is a partial negative, carbon is a partial positive. Okay, on this side we have a carbon-oxygen, oxygen partial negative, carbon is still partial positive. What happens here, though, even though these bonds are not sharing equally, because the molecule has a linear shape, meaning I have one guy tugging for the electrons on this side, like a tug-of-war, and one guy tugging over here, that linear shape cancels out any dipole moment. So this molecule has no dipole moment, even though it has polar bonds. So this will happen if we have any symmetrical geometries. So think back to VSEPR. If your geometries are any of these, linear, trigonal planar, tetrahedral, trigonal bipyramid, octahedral, and all of your x's are the same element, like in this case, both of them represented oxygen. If that's the case, even if the bonds in that molecule are polar, they're going to cancel each out like a tug-of-war. And so the molecule will be nonpolar. No dipole moment, no unequal distribution. So here are some examples. Look, bond type. So a hydrogen with an oxygen is a polar bond. They do not share equally. If I have now a molecule, if I have this H2O molecule, the shape is bent, which is not symmetrical. It's not one of those that I listed on the last page, which means the molecule is polar. So this one has polar bonds and a polar molecule. This guy, methane, carbon to hydrogen is a nonpolar bond. When we have a CH4, it is a symmetrical shape. So even if we had polar bonds, they would cancel each other out. But all nonpolar bonds in a molecule makes the molecule nonpolar. So in both of these cases, the bond type and the molecule type agree. Here's one where they don't. A carbon to oxygen double bond is polar. We get a partial positive, a partial negative. But when I put CO2, notice we get that linear shape. So the partial positives and partial negatives cancel each other out, and the molecule is nonpolar. So this example, we have polar bonds, but a nonpolar molecule. Okay, so that was mostly review on intramolecular forces, bonding, right? Polar and nonpolar was what I focused on. Now let's talk about the new idea in this video, intermolecular force. So this is when I clone the molecule, what attractions happen between those clones. And we're going to learn the different types. We're going to be able to identify them and compare them. So here are the types that we're going to focus on. We're going to learn about London dispersion, dipole-dipole, and then hydrogen bonding. All of these happen in covalent molecules, when we clone covalent molecules. And then an ionic force, like we said, happens in those ionic bonded compounds. We're not going to focus on those as much in this video. Mostly we're going to focus on the three with the stars. Okay, the first intermolecular force we're going to learn about is called London dispersion forces. And these are the weakest force, and they happen between nonpolar covalent molecules. It is important to know that everything has London dispersion, so all covalent molecules have London dispersion forces. Even noble gas elements, when they're not bonded, have London dispersion forces. Because here's what's happening before we get into this definition here. I have a molecule. Electrons from those atoms in the molecule are constantly zipping around, moving around. So it is possible that at one point in time, all of those electrons kind of are isolated on one side of the molecule. And even though it's not all the time, it's not a permanent dipole moment, right? Nonpolar covalent means they share equally. It is possible for, in these random electron movements around the molecule, for them to be kind of on one side versus the other. This, when it occurs, is called a temporary dipole. It's instantaneous, meaning it happens very quickly and then it's done. But it happens often enough that we actually get attraction between nonpolar molecules. So here's chlorine, a little Cl2 molecule, right? If I clone that guy, What I'm saying is at some point in time, the electrons might isolate themselves to one side, and that will actually cause the same thing to happen on a molecule nearby, and then we get this attraction. Even though it's brief, it happens often enough that two Cl2 atoms do have an attraction to each other. So here's a picture of this happening. This one would be on like a nonpolar atom, so like a noble gas. And this would be nonpolar molecules. It happens in the same way. We focus mostly on the molecules, but here's the idea. I have molecule A and molecule B. They're both nonpolar, right? Hydrogen to hydrogen, hydrogen to hydrogen. But if I have an instantaneous dipole for 1 second when all the electrons move to this side of the atom, I get a brief partial negative and a brief partial positive. That's great, but what ultimately happens is if you look at molecule B, when we get this brief negative and positive, the same thing will happen on this molecule. A brief negative and a brief positive. And what happens is an attraction right here, and this is my London dispersion force, my LDF. Same idea can happen with atoms. Right? Again, this is brief. This is not a permanent partial negative and permanent partial positive. It's a non-polar molecule having a partial negative and partial positive for a hot second, and then it's gone. All right, this is a fancy word, polarizability, but what it really means is it's how easy for a temporary dipole to occur. So essentially what I'm saying here is how often and how strong is it when we get this hot second dipole where the electrons are on one side and then they go back to their business, right? But the more often it happens, the easier it happens, the stronger the London dispersion forces are. Here's what we need to know. If I have a larger atom, and when I say larger, I'm not talking about mass, I'm talking about the number of electrons. So if I have a molecule with more electrons, so I say atom or molecule, with more electrons, that means it's more polarizable, meaning we're more often likely to have all the electrons kind of move to one side, which means we have stronger London dispersion forces. So if you look at this graph, here's what you need to know. Anytime we see boiling point, I want you to think of the higher the boiling point, the stronger the intermolecular force. And in this case, all of the items are non-polar molecules. Like bromine with bromine share equally, chlorine with chlorine share equally, and then helium, a noble gas, is just going to have London dispersion. So for this case, I'm also just saying that they have the stronger London dispersion force. So if you look, helium is a gas at room temperature, and it has 2 electrons. Fluorine has 18 electrons, and it's also a gas at room temperature. Same with chlorine, 35 total electrons, and it's also a gas. All of these are gases at room temperature, right? Lower boiling points, meaning they're not as attracted to each other. There's less London dispersion force. As we get bigger, right, these guys are actually liquids at room temperature, meaning they're more attracted to each other. They have a boiling temperature that we can get them to boil at, but there's more attraction because there's more electrons. More polarizable, more London dispersion forces between clones of bromine with bromine and between clones of iodine with iodine. Okay, for these guys, we're just going to look at London dispersion forces and label them from strongest to weakest. Mostly this page, I want to show you something you've never seen before just to kind of expose you in case you take chemistry in college. So this guy has a chemical formula, C4H10O2, and you can see this is a structure. This is how we draw structures in organic chemistry. Same here, C9H8O. And then C2H3N. Obviously, for some of these, we're not seeing all of the letters, right? On this guy, I see the oxygen, but I only see 1 of the hydrogens. So that means I'm missing 9 carbons and 7 of the hydrogens. Well, all of these bumps, right, all of these corner points are representing carbons, and there are hydrogens off of them. Again, you don't need to know this for our class at all. I'm just trying to expose you so you are used to seeing some of these unique shapes if you take chemistry in college. Same molecules here. What if I draw them as full Lewis structures? Obviously, this looks a little more familiar, right? We see the bonds, right? We see just covalent bonds showing the sharing, some triple bonds in there, some lone pairs, things like that. These are way more intimidating, though, than what we've seen in class. We've seen more simple drawings, but we can still figure out the London dispersion forces. Okay, back. HOC with two H's, H2CH2. So again, we're just this slide though, and we're gonna figure out London dispersion. Well, remember, the ones that are the biggest, more electrons, are going to be more polarizable, meaning those electrons have temporary dipoles more, which means stronger London dispersion. So if we look at the molecules, we have 4 carbons, we have 9 carbons. That's kind of the biggest atom we're dealing with. So this guy's going to be the largest. He has the most electrons, which means it's the most polarizable, so it has the strongest London dispersion forces. And then on these guys, we're comparing C4 versus C2, and then we have some hydrogen, some oxygen, some nitrogens. This guy is going to be our smallest, least number of electrons, so the least polarizable, so the weakest London dispersion force, and so this guy would be the middle. One other way to look at these is written out to show the order that everything bonds. So for this guy, HO, then CH2, CH2, if we look on this slide, the overall structure of how things are bonding in what order. Okay, I'm going to look back. All right, the next type of intermolecular force is called dipole-dipole forces, and this is now dealing with clones of polar covalent molecules. So if I have polar covalent molecules, they're going to arrange themselves so that their partial positive and their partial negatives attract each other. So same idea. HF is a polar covalent molecule. They share, but this guy's partially positive, this guy's partially negative, so they share unequally. You can check your electronegativity values if you don't believe me. Partial positive, partial negative. There's a clone. And notice the difference is these are not temporary dipoles, those are permanent. It is always partially negative and are always partially positive. And so then we get this attraction between the partial positive of one with the partial negative, and that's called the dipole-dipole. Here are those same scary molecules. We're going to label some of the dipoles. And really, I put the electronegativity values. And I know these are scary, but if we take it one bond at a time, it's not so bad. What we're looking for is electronegativity difference of, 0.4 or larger for there to be a polar bond. So really what kind of some tricks, a C to an H, we're going to say nonpolar. There's not a big enough difference. It's right at that 0.4. And then anything with the oxygen and the nitrogen is going to be polar. So like we can label different sections of these. Here's a hydrogen with an oxygen, that's positive to negative. Okay, a carbon to an oxygen, he's the positive, oxygen's more electronegative. If you look at the numbers, 3.5 versus 2.5, same thing over here. On this guy, carbon to hydrogen, carbon to hydrogen, carbon to carbon, same thing, right? They share equally, so none of these count, right? That makes this molecule a lot easier. Okay, carbon to carbon, now we can look, carbon to oxygen, and C to H is equal. C to H is equal, right? I'm ignoring all of these C to H's, but carbon to nitrogen has a dipole moment. So I kind of color-coded here. The red sections are nonpolar sections of the molecules, where that chunk of the molecule is sharing equally. So these reds are nonpolar, whereas the greens are polar, or sections of the molecule where things are being shared unequally. The idea, though, is even though these are more complicated than what we're going to look at in class, I want you to just understand that you can have molecules that the entire molecule is polar or the entire molecule is nonpolar. But in more complicated cases, it's possible that there are sections that are polar and sections that are nonpolar. Okay, the bigger the difference in electronegativity, the stronger the dipole. So this guy has 2 places on the molecule where it can dipole-dipole interact. So if I clone this guy, it has double the opportunity. So really, this guy has the strongest dipole-dipole. And then we could compare the other 2 pieces for dipoles, and what we would look at is the difference in electronegativity. The one with the larger difference is able to have a stronger dipole-dipole attraction. Okay, before I even start this slide, I'm going to put little quotes around the word bonding because these are still intermolecular forces, so between the clones of the molecules. But it has the word bond in it because whoever made this up hates high school students and likes to confuse them. So here's the idea. If I have a dipole-dipole attraction that is extra strong, we give it a special name called hydrogen, air quote, bonding. Okay, how do I know if a dipole-dipole is extra strong? It's going to have in the molecule a hydrogen covalently bonded to a nitrogen, an oxygen, or a fluorine. So this is a covalent bond in the molecule. I'm talking about how this guy, hydrogen, oxygen, hydrogen, has a covalent bond in the molecule. Then if I clone that molecule, the hydrogen air quote bond attraction is between that special hydrogen with an oxygen, nitrogen, or fluorine in the opposite molecule. Why is this stronger than dipole-dipole? Well, hydrogen bonded with either of these 3 is a very, very polar bond, and if we have a small size happening, it allows this hydrogen to get really close to the oxygen of the other molecule. So it's the strongest type of intermolecular force we're really going to focus on because it's a special version of dipole-dipole. So here's some complicated molecules. We got one where the hydrogen is covalently bonded to the nitrogen. Same with this molecule. Notice the attraction in red, this is the hydrogen bonding, is between the hydrogen and the nitrogen in the other molecule. These guys are hydrogens, but they are not capable of hydrogen bonding because they are not covalently bonded to the F, O, or N. They're bonded to a carbon. So those guys are not capable of forming hydrogen bonds between clones. Same idea happening here with water, special hydrogen attracted to the nitrogen. You guys actually learned about hydrogen bonding in biology class. So when we have our DNA double helix, we know that the base pairs are attracted to each other. For example, guanine, cytosine, adenine with thymine, and it's actually hydrogen bonding, and I should put air quotes, right? Attraction that holds those guys together. So it's not an actual chemical bond, it's an attraction between the different molecules, between the special hydrogen in one of the base pairs with an oxygen, nitrogen, or fluorine in the other. And yes, these are strong, but we know that they can be ripped apart. I don't remember what the guy is called, but he can go through and kind of break all of these so that we can replicate the DNA. There are also hydrogen bonds in your hair. So different side chains in your hair. If you've ever had split ends, that's the hydrogen bonds actually breaking in your hair and it's splitting. So we now have learned about the different types of intermolecular force. How do I kind of identify? Well, first, we're going to not worry about the ionic forces, the ion. Okay, if it's an ionic compound, it has ionic forces, end of story, we're good. But here's what we do. First, I'm going to look at a single molecule and see if it's polar covalent or nonpolar covalent. If it is a nonpolar covalent, then if I clone that molecule, there will be London dispersion forces between those clones. If it is a polar covalent molecule, it's going to have dipole-dipole or hydrogen bonding. How do I know? If the molecule has an H bonded to an F, O, or N, then it'll be hydrogen bonding. when you have the clones, or if it doesn't, it'll be dipole-dipole. Polar covalent molecules do have London dispersion forces, but these two are so much stronger, those are the ones we focus on. So looking at the strengths, the weakest force of attraction is London dispersion, then dipole-dipole, then hydrogen bond, and then those ionic forces, again, that we're not stressed about, those are the strongest of all the forces. Okay, the last segment of this video is about properties, so what properties are impacted by intermolecular forces. So here are some of the properties we're going to focus on in this class: boiling point, surface tension, capillary action, viscosity, and vapor pressure. If you have stronger intermolecular forces, that is going to increase these abilities. If you have weaker intermolecular forces, you're going to have lower levels, lower boiling points, surface tension, things like that. So let's talk about boiling point. First of all, the boiling point is the temperature, so it's actually a temperature that we go from the liquid to the gas. So in this case, we are doing a separation, right? I am separating liquid molecules to the gas. So if I have strong intermolecular forces, it is going to be hard for me to separate from liquid to gas, a higher temperature. Here's the main idea. If I have a high boiling point, which is a high temp, I'm a molecule with strong intermolecular forces. It took a higher temperature for my intermolecular forces to be broken when I went from liquid to gas. A lower boiling point, a low temp, means it's a weaker intermolecular force. Surface tension is the next property we're going to look at. It is this resistance for increasing a surface area in polar molecules. So for example, here's a polar molecule. It is attracted to all of these molecules around it. On the surface, though, look at this red guy. He only has 3 molecules that it can actually have an intermolecular force with. So if I'm a molecule with strong intermolecular forces, well, that molecule with strong intermolecular forces will have a high surface tension. Okay, what that means is it is pretty difficult to break that surface because it's so strongly attracted to those molecules near it. Whereas something with a low surface tension will have weaker intermolecular forces. Water has a pretty good surface tension. You can see lots of bugs with the ability to walk on water, right, without breaking that surface tension and falling through. I also think of like maple syrup, even higher, even stronger intermolecular forces. If you've ever been to like an IHOP or anything and tried to pour the syrup out of the dispenser, it almost feels like there's like a thin layer that you have to break through when you're trying to pour that syrup. Capillary action is the spontaneous rising of a liquid through a narrow tube, so like sponges, filter paper, trees absorbing water. Adhesion is the attraction between a liquid and its container. So water, like this guy, has adhesion. That's why we get this meniscus, because the water is actually attracted to the glass of this graduated cylinder, whereas mercury doesn't have a lot of adhesion. You can see it actually is more attracted to itself, which is cohesion, than it is. You get like almost an opposite of the meniscus. Viscosity is the resistance to flow. So I think of like pouring out, if it pours easily or not when I think of viscosity. And something with really strong intermolecular forces is not going to flow very easily, which we say has a high viscosity. So this guy is called glycerol. It has 3 different positions where it is capable of hydrogen bonding. It has a very high viscosity, meaning picture it like a thick liquid. It won't pour as easily. Something with a low viscosity, less intermolecular forces, it flows really easily. You can pour it straight out of the container really easily. And the last one's vapor pressure, and this one actually feels kind of opposite of the others. So normally what happens is on the surface of a liquid, we're going to get some evaporation. But if I close that container, we are actually going to establish something called equilibrium, where the gas goes back to the liquid and some of the liquid goes as a gas, and it's this equal back and forth where you actually don't notice a difference. At some point, the pressure above this gas is going to be constant. That's when we reach the equilibrium. That pressure is called the vapor pressure. Something with weak intermolecular forces means, that a lot of these gas particles, or these liquid particles, turns to gas. That's the high pressure, which means that the particles weren't that attracted to each other as a liquid. So it's actually weak intermolecular force when there's a high pressure, and then the opposite. A low vapor pressure means a stronger intermolecular force. I know this was a ton of information. We will do practice in class and we'll go through some of the more finer and more important details, but I wanted to give you an overview and give you all the vocab in this video.